Welcome back. So my name's Rob, and this is Introductory Statistics for the Psychological Sciences. And today we're going to be going over independent groups t-tests. We'll talk about the conditions under which it's appropriate to conduct an independence group t-test. We'll compare those conditions to other types of t-tests and z-tests. And then we'll go through an example of how to compute a independent groups t-test, how to compute the effect size, how to compute a 95% confidence interval, and then finally how to ball it all together and report your results in an APA-style results narrative. So, as always, if you like this video, please like it, subscribe, and don't forget to hit the notification bell to get updated when new videos just like this one come out. And if you have any questions, don't hesitate to leave them in the comment sections below. As always, over here are our PowerPoint slides, and up here is our virtual whiteboard, and we'll use the whiteboard to do these hand calculations together. So I guess let's just dive in. So during the last lecture, we discussed distinctions between within subjects and between subjects research designs. And so I wanted to briefly review some of that content here. So we call a research design a within subjects design whenever all participants receive both levels of the independent variable, or all levels of the independent variable. In other words, we're taking repeated measurements of people over time, right? So a within subjects design is also frequently referred to as a repeated measures design. But basically all this means is we're taking multiple measurements within the same people. So all individuals get all conditions for a within subjects or repeated measures design. Now, whenever our independent variable only has two levels, right? Meaning it's a categorical independent variable with two levels. We have two means. We're going to use a correlated groups t-test to compare those two means collected on the same person. Now, an advantage of a within subject research design is that it has greater statistical power because we control for individual differences. Essentially, every participant acts as their own control. And as a consequence, we need fewer participants to obtain the same statistical power as we would with a between subjects design. Now, a between subjects design is whenever each participant only receives one level of the independent variable, right? So it would be like we randomly select people from a population and then randomly assign them to either condition A or condition B. So each person only gets one group. This is probably what most people think of whenever they think of a scientific experiment, right? Where you might have one group as the placebo group or control group, and one group as like a treatment group, or where you're giving them some kind of thing that you're interested in to compare against the control group. And so this is called a between subjects research design, right? Or an independent groups research design. And the reason we call it this is because we're looking at the variability between two groups of different subjects, right? Two independent groups. And in this way, we establish baseline group equivalence on the basis of random selection and assignment. So essentially, when we randomly select and assign participants to one group or the other, it's assumed that those groups, as our sample size increases, are going to approximate like a normal distribution. And the likelihood that, some weird person would be in group 1 is equal to the likelihood that they would be in group 2. So when we have a sufficient sample size, we can assume group equivalence. And that allows us to compare one group mean to another group mean, both of which contain unique participants. So it's this second type, this between subjects research design, where we would, if we had two means, so two samples of people, and we wanted to compare those two means to see if they were different, this is the condition under which you would use an independent groups t-test. So it's also called an independent samples t-test. This is whenever we compare two independent groups. Each participant can only be in one group, and all participants only receive one level of the independent variable. Okay. So, as with all t-tests, our dependent variable needs to be a quantitative variable. And the way you know when you're going to conduct an independent groups t-test is whenever you have an IV that is two levels, so it's qualitative, right? And there's two groups, and it's a between subjects design such that each person is only in one group or the other group. And what the independent samples t-test allows us to assess is whether the mean difference between the two samples that we have is different over and above what you would expect by chance alone. So importantly, as with all t-tests, we're in the domain of inferential statistics. And inferential statistics are used to make inferences about populations from samples. So what we're actually comparing aren't necessarily sample means, but the populations. We're evaluating whether or not this difference would occur in the overall population. So let's look at the formulas that we've had thus far for the various types of mean comparison tests. So we have a one sample z-test where we had a mean difference, the difference between a sample and a population mean, over the population standard deviation divided by the square root of n. And that was great. That's where we kind of started this mean comparison game from the get-go. And then we kind of kicked off a training wheel, right? So we took away the population standard deviation, right? And so you can see for the one sample t-test, right? It's essentially the same thing. You're comparing a sample mean to a population mean. However, in the denominator, you do not have the population standard deviation. Rather, you have to estimate it, and you do so using the sample standard deviation. And then we moved into correlated groups t-tests. And as a refresher, a correlated groups t-test is basically the same thing as a one sample t-test. However, conceptually it's unique because what you're comparing is the difference between two means in a repeated measures design or a within subjects design. And you're comparing that difference to a population mean of 0, right? And so then you're dividing in your denominator, you're dividing by the standard deviation of the differences, of the different scores. But as you can see, the top 3 tests indicated on this slide are almost all identical. Now, the independent groups t-test, which we're going to cover in detail today, is a little more different. Now, in theory, it's the same. It's still a mean difference over error. However, now we have 2 samples. So we have to pool the variance of those 2 samples in order to get an accurate estimate of error. And so you can see here, we have our t obtained value is equal to the difference between the 2 sample means we have. And then we compare that difference to a population difference of 0. That's very similar to a correlated groups t-test. And then we divide by the standard error of the difference between means, which is this S sub x bar 1 minus x bar 2. Okay. Now those are the equations that are more kind of conceptual in nature. If you have the standard deviations, all of this. Here's what you would use if you were computing t obtained values or z obtained values whenever you were just given raw data. So we can see that, looking at the one sample t-test, we've got a sum of squares. We're dividing by some metric that takes into account sample size or degrees of freedom. And it's the same with the t-obtained value for the correlated groups t-test. And then when we look at the independent groups t-test, that denominator looks pretty gnarly. But really what it is we're simply taking into account the sum of squares for both sample means that we have. And we're dividing by essentially the metrics of sample size or degrees of freedom. So conceptually, we are doing the exact same thing. And I think this is very important for this to click. All we're doing is looking at a mean difference in units of some type of error metric. And that error metric helps us, protect against claiming there's going to be a difference whenever the magnitude of the effect is not likely to hold in the population or is likely due to chance. So, okay, let's do an example of an independent groups t-test. And the example topic is going to be trying to induce empathy or empathic behavior in bonobos. So, there's two very empathic bonobos. Let's see if we can do it. Okay, so here's the problem. A primatologist investigated whether differences in the reward structure of a game played by bonobos would increase their subsequent empathic concern for others. In condition 1, bonobos engaged in a cooperative game together in which winning led to a food reward. This is the self-reward condition. In condition 2, bonobos engaged in the same cooperative game, but their cooperative partner would receive all the awards, such that doing good would only help others. This is the other reward condition. After the task, the bonobos were allowed to freely socialize, and the researcher computed the average minutes the bonobos spent grooming each other. The experiment was conducted using 30 randomly selected bonobos who were randomly assigned to one of the two experimental conditions, such that 15 were trained in the self-reward condition and 15 were trained in the other reward condition. Is there sufficient evidence to indicate that the self-rewards increased empathic concern among bonobos? Okay. So, here is the data we collected from these 30 bonobos. We have, and again, this is how many minutes they spent grooming one of their companions after the cooperative game. So what we're going to need to do with this data is the sum of squares, where we create a column of the squared measurements, and we'll use this down the road. But importantly, we have to do sum of squares for both conditions, for both samples. Okay, so what are the steps to conduct an independent groups t-test? Well, it is exactly the same procedure as every other test we've done up to this point. So the first thing we need to do is we need to set up our hypotheses. So when we're doing hypotheses for an independent samples t-test, basically what we're doing is we're making the null and alternative hypothesis comparing two different population means instead of comparing one sample mean to a population mean. So basically, we're saying that the null hypothesis says that the two samples are random samples from populations that are equal. In a directional, we're going to say that the two samples are random samples from populations where one population is greater than the other or less than the other. And for non-directional, the two samples are random samples from populations where the populations are simply not equal, so reflecting a difference or change without any kind of directionality. So let's write out our null and alternative hypotheses for this problem. So our null hypothesis is going to be that mu of group 1, which is the self-reward condition, is equal to mu of group 2. So again, the null hypothesis is simply saying there's not a difference. The alternative hypothesis is going to be that mu of group 1 is in some way related to mu of group 2. But let's go back and look at the question that we're working with. What was the specific question? So at this last sentence, it says, is there sufficient evidence to indicate that the self-rewards condition increased empathic concern among the bonobos? So this word increased indicates that this is a directional test. And since our dependent variable is the duration that bonobos engaged in grooming behavior after the cooperative game, right? Increased empathic concern would mean a longer duration of grooming. So we're expecting that the bonobos in the self-rewards condition are going to have a higher duration than the bonobos in the other reward condition. So because of this, we're saying that mu1 is greater than mu2. Okay. Okay, so here is a sampling distribution of the difference between mean scores, right? And so essentially what we are doing when we're testing this hypothesis is we're comparing the difference between our two sample means to a population difference between means of 0, right? So this is similar to the logic behind the correlated groups t-test, but we're testing to see is our difference between sample means different from 0. So the next step is we need to determine the critical value of t. Before we do so, we should always draw out our normal distribution. Okay. And this is a directional test where we're looking greater than, we're looking up here. So this shaded area is our region of rejection. And because it wasn't stated, we can assume that alpha is going to be 0.05 in that area. And again, this t-crit value is this line right here that cuts off this proportion of 0.05 in the upper tail. So we need to pull up our t-table. And so let's see, how do we figure out for an independent group's t-test what that critical value is? Well, we're going to use this same t-table, but our degrees of freedom calculation is essentially computed differently. Basically, because we're computing using two different standard deviations or two different samples in our denominator, right? Each sample has a -1 degree of freedom, right? So if you remember in a correlated groups t-test, we were dividing by n minus 1. In one sample t-test, we're dividing by n minus 1. That's because there's 1 degree of freedom. However, here we have 2 samples, and each one dings us with one degree of freedom. So the degrees of freedom for an independent sample t-test, because we have 2 samples, is the total number of people minus 2. Or put another way, it's the number of people in sample 1 plus the number of people in sample 2 minus 2. Now, so there's some new nomenclature here to describe sample size. So we have a big N, which represents the total sample of everyone in the experiment. And then we have little n, and little n represents the number of people in one sample. So in this instance, big N is going to be 30. We had 30 bonobos. But little n is going to be 15. We had 15 in each group. So our degrees of freedom for an independent groups t-test is big N minus 2. That means that we have 28 degrees of freedom, right? So a total of 30 minus 2. So now that we know our degrees of freedom, and we know that we're looking for the cutoff that divides off a proportion of 0.05 in the tail, we can look at our 0.05 column here, and then 28 degrees of freedom here, and we get 1.701 right here. So this is our critical value of t. It's the t value that divides off this 0.05. So t crit is equal to 1.701. Okay. So now our next step is we are going to set the decision rule for our hypothesis test. And again, this just tells us under this condition, we will reject the null hypothesis. And if that condition isn't met, then we fail to reject the null hypothesis. So our decision rule is going to be reject the null if t obtained is greater than or equal to 1.701. Okay, so we've set our criteria, and now we need to compute the obtained value of t, and then we'll compute the effect size, and then we'll compute the 95% confidence interval for this mean difference. Okay. So here is our t equation again. So we start off and we've got t obtained is equal to the difference between the two means divided by the square root of the sum of squares of sample 1 plus the sum of squares of sample 2 divided by number of people in sample 1 plus number of people in sample 2 minus 2 times 1 over n plus 1 over n, the little n's representing their respective samples. So let's move along here. So this is a more conceptual way to frame it. We've got the t-obtained value is this mean difference divided by the standard error of the difference between means. So again, mean difference over error. So let's write down this t equation. T obtained is equal to x bar 1 minus x bar 2 divided by the standard error of the difference between means. Now you might be wondering, why didn't I have in the numerator, why didn't I subtract the mu of x1, x bar 1 minus x bar 2? Well, that's 0, so it just kind of is redundant. Okay, so again, this denominator is the estimated standard error of the difference between sample means. And here we've got another formula. So we've got the standard error of the difference between sample means is equal to the square root of this SW squared, which represents the pooled variance of both samples, times 1 over n1 plus 1 over n2. Okay? So let's continue. Now, how do we compute the weighted estimate of our population variance, or the pooled variance? Well, this is where we have to do sum of squares. So SW2 is equal to the sum of squares for sample 1 plus the sum of squares for sample 2 divided by the sample size of sample 1 plus the sample size of sample 2 minus 2. So you may notice that the denominator there is the degrees of freedom for the test. Okay. Now, what was the sum of squares? Well, we've done this for just about every test we've had. Sum of squares for sample 1 is equal to the sum of x1 squared minus the sum of x squared divided by the sample size of sample 1. And the sum of squared for sample 2, same thing. You know, nothing different here. Okay, we're just kind of setting this up. As you can see, we're going to have to work backwards quite a bit. Okay, so let's look at our sample data again. So you can see here we have a column containing the mean number, or the number of minutes each bonobo spent grooming one of its friends after it did the cooperative game. And we have it for both the self-reward condition and the other reward condition. Now, just like before, whenever we would compute sum of squares, we're going to create the sum of each of the sample columns and the mean. And then we're going to make a column where we square the values in the self-reward column and then sum those up as well. Now, importantly, you have to do this for both samples now. Okay, so let's compute the sum of squares for the self-reward condition, which was condition 1. So we have the sum of x squared, which is going to be 586.31, minus the sum of x, which is 93.3, squared, divided by the sample size of that sample, which is 15. And this is going to give us 586.31 minus 580.326. And so our sum of squares for sample 1 is equal to 5.984. Okay, now let's do the same thing for sample 2. So for sample 2, we have the sum of x squared, which is 450.19, minus the sum of x squared. So the sum of x here is 81.70 squared divided by 15. And this is going to give us 450.19 minus 444.99. And so that leaves us with our sum of squared for sample 2 is 5.2. Okay, so now that we have our sum of squares computed, we can plug them into our formula, or intermediate formula for the pooled variance, right? So basically, we're going to put our sum of squares here and our sum of squares for the second sample here. And so we're going to get 5.984 plus 5.2 divided by 15 plus 15 minus 2. And again, that's the degrees of freedom. So this is going to give us 11.184 divided by 28. And that is equal to 0.3994. Okay, so now we have our pooled variance, and we can plug that in to our estimated standard error of the difference between means formula. So we will get the square root of, and again, 0.3994, 0.3994 times 1 over 15 plus 1 over 15. And this is equal to the square root of 0.3994, times 0.1333. So this gives us a standard error of the difference between means of 0.2307. Okay. So now we have our denominator for the t equation. So we come back up to our t, and we report the mean of sample 1, which is 6.22, minus 5.45, divided by our standard error of the difference between means, which is 0.2307. This computes out to 0.77 divided by 0.2307, which gives us a t-obtained value of 3.3377. Okay, great. So we have our t-obtained value. Now what we need to do is compute our measure of effect size. So when we compute our effect size, we're going to use Cohen's d, just like before. And our estimated d value is going to be the difference between the two sample means divided by the square root of the pooled variance. So we can simply plug in our values. We have d, estimated d is equal to the difference between means, which if you look, you can just, that's just the numerator of the t equation, is 6.22 minus 5.45 divided by the square root of the pooled variance. Well, we already computed the pooled variance. Remember, it is right here, and we got 0.3994. 0.3994. So we simply resolve for this, and we get 0.77 divided by the square root of 0.3994, which is 0.77 divided by 0.6320, and this resolves down to an estimated d value of 1.22. Okay, so if you recall, going back to our chart of whether this is a small, medium, or large effect, this is a quite large effect. It suggests that the difference between these two means is essentially 1.22 standard deviations apart. So that's a considerable difference. Now we need to move on and conduct our 95% confidence interval. So the confidence interval formula is conceptually still the same. However, it's mathematically slightly different. So we want to be able to construct a 95% confidence interval for the difference between these two means. And remember, a confidence interval is simply a point estimate. It's essentially our best guess at the population mean, which is our sample mean. And then we're looking at a margin of error above and below that. So we're trying to say, what is the range at which 95% of the time the population mean will fall given a particular sample mean. And so we have the lower boundary of that confidence interval is equal to x1 minus x2, the sample means, minus the square root of the standard deviation squared, in other words, the variance, of sample 1 over n of sample 1, plus the standard deviation squared of sample 2 divided by the sample size of sample 2, times the t value that will cut off 0.025 in the tail. So again, we're looking above and below here, and for it to be 95%, we need to cut off 0.025 in each tail. So we're going to need to compute the standard deviation for each sample so that we can plug it into this confidence interval equation. Now, I'm sure you are very familiar from earlier in the semester when we computed standard deviation. And essentially, what we did was we took the sum of squares, divided by n minus 1, and then took the square root of that. So for sample 1, to get our estimate of S1, we have the square root. We already computed the sum of squares for sample 1 of 5.984. I'm getting that right here. Divided by 15 minus 1. So this is going to be equal to the square root of 0.4274, and that is equal to 0.6538. So we have a standard deviation for our sample of 0.6538. Now we need to do it for our second sample. 5.2 divided by 15 minus 1 is equal to the square root of 0.3714, which is equal to 0.6094. Okay. Now we simply need to plug this into our equation for the lower and upper boundaries of the confidence interval. So, mu of lower is equal to x bar 1 minus x bar 2, which is the numerator of our t equation, 0.77, minus, and then the square root of our sample 1 standard deviation, 0.6094 squared divided by 15 plus 0.6538, which was the sample 2 standard deviation, divided by 15. And then we need to multiply it by the t value that will cut off 0.025 at the end of each tail. And when we do this, we're going to use the smallest degrees of freedom for each sample. So if we had one group that had a degrees of freedom of 13 and one group that had a degrees of freedom of 20, we would use degrees of freedom 13 in our table. We'd go with the lowest one. But so let's look. The degrees of freedom for each sample in this example are equal, right? And so our degrees of freedom for sample 1 is n minus 1, which is 14. There's 15 bonobos in each group. Minus 1 is 14. So we need to look at our t-table. And again, we want to cut off 0.025 from each tail. And we're looking at a degrees of freedom of 14. So we can see that the cutoff is 2.145. So the cutoff for our t of 0.025 is 2.145 times 2.145. Okay. So now we can just resolve this equation for mu lower. So this is going to resolve to 0.77 minus the square root of 0.0248 plus 0.0285 times 2.145. And this is equal to 0.77 plus, or I'm sorry, minus the square root of 0.0533 times 2.145, which is equal to 0.77 minus 0.4952, which is equal to 0.2748. So this is the lower bound of our 95% confidence interval. Now for mu upper, the equation, the only difference between these two equations is that for the lower bound, we're subtracting from our difference between means, and the upper bound we're adding. But you can see that the formula beyond the first plus or minus sign is identical. So we've already done this math, right? So right here, we resolved all of that down to 0.4952. So here we can just say 0.77 plus 0.4952. And so this gives us a upper boundary of 1.27. So our 95% confidence interval is going to be the lower bound of 0.27, comma, the upper bound 1.27. Okay. Well, that was a lot. So we have computed our effect size. We've computed our confidence interval. Now, we can say with this confidence interval that we are 95% confident that the mean difference between sample 1 and sample 2 is between the lower and upper bounds of this confidence interval. So on the basis of this, now we move forward to determine whether we should reject or fail to reject the null hypothesis. So we need to go back up to our decision rule. Our decision rule said we'll reject the null if t obtained was greater than 1.701. Well, our t obtained value right here was 3.3377. So that is greater than 1.701. That means, our mean difference was way out here. So we reject the null and provisionally favor the alternative hypothesis, which is that there is a difference between the empathic concern that bonobos express based on whether or not they were in the self-reward condition or the other reward condition. So now let's write this up in APA style. So we're going to start out with, what did you do? So an independent group's t-test was conducted to determine whether the reward structure of a game played by bonobos would increase their subsequent empathic concern for others. Specifically, we tested whether bonobos who played in a cooperative game to win rewards for the self would increase empathy relative to bonobos who played the same cooperative game but won awards for their partner. And then for what did you find? Compared to those who played to win rewards for their partner, and then we report the mean and the standard deviation of that sample. Bonobos who played to win rewards for the self, and again the mean and standard deviation, demonstrated significantly increased empathic concern, as indicated by subsequent duration of grooming behavior. And then we report our t obtained value. And after that t value, we put the overall degrees of freedom for our independent group's t-test. So remember, the degrees of freedom for this test was the sample size minus 2. So that's 30. Both samples, everyone in the study was 30 minus 2, and we get 28. Then we report our t obtained value. And we say that the probability that we would get this result due to sampling error is less than 5%. Right? So that's good. It means that we have confidence that this mean difference would not likely occur due to chance alone. And then we report our 95% confidence interval. So this says that the population, the difference between these two means in the population is going to fall somewhere between 0.27 and 1.27. And then we report our effect size, Cohen's d, of 1.22. And we state the magnitude of the effect. And in this case, it's a large effect. And then we go to, what does it mean? We say this pattern of evidence indicates that self-focused rewards for cooperative play could increase subsequent empathic behavior among bonobos more than other focused rewards. Okay, and then we just take that, we put it all together, and we have a full APA-style results draft. And this is precisely the type of writing that you would see in an APA-style peer-reviewed scientific manuscript that reported an independent group's t-test. Well, I hope that this lecture was helpful. If you have any questions, please don't hesitate to leave them in the comments section. If it was helpful, like and subscribe. And thanks for playing. I look forward to doing this again next time. Okay.